Okay, I guess now the recording is on. Okay, so now in the data intensive task, basically it depends on memory and memory speed and memory bandwidth. So if you remember from the examples we were doing just a couple of lectures ago about finding out EMAT, you would have realized that the memory bandwidth also plays a major part. So your memory may be large, maybe very fast, but suppose your bandwidth, which brings in your memory from memory to your processor, is just, or between various memory modules, is just say 256 bits or 128 bit, then naturally your computer would run slow. So for data intensive task, it is mainly your memory and it's basically speed and bandwidth which counts. For compute intensive task, it is mainly, I can give you an example of say calculation of the value of pi using Monte Carlo method. So there is just one formula and you run it again and again on the output. Output goes back to input. Again, you do it so that your value of pi becomes more and more accurate with more and more places after decimal point. So there, it is your processor speed. So, then someone may ask you this question that, should I buy an i5 computer with say 8 GB or 16 GB of DDR4 RAM and, certain amount of cache, or should I buy i7 with lesser amount of RAM? Then your answer should be that it depends. And if someone presses you that what does it depend on, then you say that is your task mainly data intensive or compute intensive? If it is a mix of both, then you say that buy whatever you can afford. i7 with large amount of RAM would be great. If you don't know whether your tasks are going to be data intensive or compute intensive, so buy expensive hardware for both. If you are sure that your laptop or your mobile device is going to be used for one or the other, say for web browsing, then it is a data intensive task. Then you just go into that particular site. So another application would be image processing. When you take picture through your camera, it could be your mobile phone camera or standalone camera. Massive amount of data would come in, and then your processor has to do some kind of processing on it. And faster it processes, better results you will get, because it has to do some enhancements. And there are HDR techniques and various other techniques where your image has to be modified or massaged, or you have to make certain changes or smoothing out some outlines. All those things are examples of image processing, and you have to take in large amount of data quickly, because there is one click of the shutter, and whatever data comes in, you have to accept it and work on it in real time. So those are all data intensive tasks. And then in high performance computing, you will find many examples of compute intensive tasks. And one example I already gave you, where you don't require too much data from outside. You keep on doing the same operation over and over again on limited set of data. That would be a compute intensive task. So your recommendation of a computer system would depend on what task you are doing. So that is number one. Number two, I wanted to tell you that suppose, what is the relationship between CPU, GPU, DSP, and some kind of AI accelerator? Right, so these are all, basically computing elements, right? GPU does computing, DSP does computing, AI accelerator does computing. And CPU, of course, it does the computing. The whole idea is that, CPU acts as a manager. So what would happen is that, this is your CPU. And, these are known as co-processors. So they don't work independently. I mean, they have to have a CPU to make them useful. So, your GPU is, say, NVIDIA GPU of some kind, which is over here, say GPU. This is your CPU. Then, you have got DSP. And, you have got AI coprocessor. Instruction stream would come to your CPU, right? And then CPU would decide that, this particular instruction sounds like a media instruction, something to do with graphics. So let me send it to GPU. So it will toss it over to GPU. Or it may think that, something to do with voice. So it may send it to DSP. Or it may think something to do with machine learning or artificial intelligence, and it will toss it to AI. And, I told you last time, I gave you one example in the very beginning of the semester that, you got your system and, you are playing a video game. In your video game, you are shooting a gun at something, or, you're throwing a grenade. Now, when you throw a grenade, I mean, you want some realistic effect. So, you want people falling down, or, you want buildings to topple over, or, you want trees to fall down. Now, and then, appropriate sound should come out so to make you feel that it is something which is realistic. So your CPU will get this instruction stream. Then it will send whatever it has to go to GPU. It will send it to GPU. Whatever has to go to DSP, it will go to DSP. And then, all these things would send things to a buffer. Your GPU results will come to a buffer. DSP result will come to a buffer. And what you want is a seamless integration of all three, that is CPU, GPU, DSP. So, you want to hear a large explosion. You want to see an explosion. You want to see trees being thrown away, down, or, walls falling over, or, whatever, people falling over in a particular direction based on the physics of the explosion. And then, you also want to see the visual effects. So your GPU would be calculating the physics that, which way the tree should fall. So if the grenade is coming from this side, then, tree should fall in the opposite direction. So, and GPU will have to render the image, how things would look after that boom. And, maybe one image, after every few microseconds, so that, you get a nice smooth rendering. And AI may be, figuring out that, what would be your next move, or, what should be the ideal thing, or which way your character should run, or which way your enemy should run. So all these things has to work together. And, even if you have very powerful GPU and, a lame CPU, then, your performance would be determined by the lowest of all three. So again, once again, it makes a good sense to match all the devices. So if you have a state-of-the-art GPU, but, if you don't have a powerful CPU, then, things would not be running as smoothly as you wish. You may feel that, oh, I got a GPU which is so nice and, so expensive, but, it is not giving me a satisfactory result. But then CPU also has to be powerful enough to take work or to assign work to GPU and get the desired result. Same thing goes with DSP. Now, as I told you last time that, in the end, what does GPU do? It does matrix multiplication. What does DSP do? It does matrix multiplication, sort of. And what does AI do? It also does matrix multiplication. Can CPU do the same? Yes, it can do the same. But as CPU is a general purpose computing element, it does not have a specialized array of doing matrix multiplication, whereas GPU has got hundreds of computing elements, right? So it has got like, maybe 1,000 processors, each running at a slower speed, not as fast as CPU, but it has got 1,000 elements. And you make 1,000 threads or 2,000 threads and send 1 or 2 threads to each. and then, find the result and, combine them. Because I told you that image processing, or for that matter, matrix threads as you like. So in reality, you can have as many processors as you have pixels. So, I mean, that would be, but you may have very large number of pixels, and you can't have realistically that many number of computing elements in GPU. But the idea is, and if I want to explain you in a layman's term, if you see a picture, a pixel on one corner of your image has nothing to do with another pixel somewhere else. So you can do independent calculation of each one of those pixels, and in the end, just collect the answers, and you will get the complete image. Similarly, even in a video, one frame has nothing to do with other frame, because in other frame you have to do the calculations again, because some things may have moved, some things may have been erased, or you have turned your camera angle so that now you see new things. So once again, you can even do frame calculations independently. So each frame can be calculated independently. So that means that matrix multiplication in general, and graphics and other things in particular are very amenable to parallel processing. So that's why your GPU has got hundreds of processing element, whereas your CPU has at most 8 cores right now. We are not talking about supercomputers or processors which are used in server, which may have 96 cores or more, because there you have powerful AC, temperature control, humidity control, so that your heating is well within control. Whereas in CPU, normally it is running at say 3 gigahertz or 2.8 gigahertz. In your mobile phone, it would heat up in just 2 minutes if it is running at full speed. So after 2 minutes, the speed will have to go down for CPU inside your mobile phone, whereas your GPU will not heat up that much, nor would your DSP. So, I mean, these are the things which you need to know, because these are very practical things, it can be asked to you in your interview question. So you should remember how CPU, GPU, DSP, AI accelerator, or other kinds of accelerator, they work in conjunction. So once again, CPU is the manager, and other things are known as co-processor. CPU assigns them work, and in the end it collects them. How it is collecting it, I mean, that is a pretty complicated thing, and you can understand that when you become a designer or study computer architecture in great detail. But right now, for the purpose of this class, you do understand that there is some kind of buffer where each one puts the result, and CPU again is finally in the one which does the calculation of physics, tells the answer to GPU, asks it to do the rendering of the image, asks DSP to generate a noise or a sound, and then seamlessly connects all three, so that it feels to us that we are watching a movie where everything is happening just like what would happen in real life. Does anyone have any question up to this point? Okay, I thought people would be interested in knowing what is happening in real life. Okay, probably you can think about it, read about it, because I mean, this is what you will be working. Whether you go into computer science, or whether you go into image processing, or whether you go into VLSI, either you would be using it or designing it. Okay, so let me move on. If someone has any question, you can ask me later. Let us start with a new topic. This topic I deliberately skipped for later, and now I'm bringing it back. And that topic is Just 1 second. Okay, so we are going to talk about branch prediction. Now, in branch prediction, we normally, this is, probably 1 second. See, first of all, let us understand the idea of branch prediction. So if you remember, I kept on giving you this example that, you have got, again, let's use our faithful 5-stage pipeline. Now, you are putting in a program, which is something like, this program is several instructions long. I forgot to write for. And there is a loop over here. Now, normally, as I told you, what would happen is that, you would be, and then number 5 is a conditional execution statement. Conditional statement, right? So that would tell you that, if the condition is met, you come out of the loop. If the condition is not met, you go back to instruction number 1. So, you put in instruction number 1, then, in the second cycle, you shove in instruction number 2, where instruction number 1 would be at decode stage. Then in the third cycle, you shove in instruction number 3 will be fetched. Then 2 would be here and 1 would be here, and, so on and so forth. So when 5 comes in, it would be like, 5, 4, 3, 2, and 1. Instruction number 1 would be in write back stage, 2 would be in memory stage, and so on. After 5, in the next cycle, when 5 moves over here, and 1 is already written, so it is retired, that particular instruction. Then, the question is which instruction to fetch. I mean, the program counter doesn't know whether it has to go back to instruction number 1 or it has to go to instruction number 6. So in absence of anything, it will bring in instruction number 6. And why it would do so? Because instruction number 5 has not yet been executed. It will be executed in the next cycle. So in the next cycle, 5 will enter execution, 4 will be in memory stage, 3 will be here, and then 2 will be retired. 6 will come to decode. And once again, since 5 has just entered the execution stage, number 7 will come here. And in the next cycle, when 5 is executed, then it would realize, then, a signal would go to program counter. That, program counter, instead of getting PC gets PC plus 4 bytes or 1 word. Normally this would do unless, this input comes in. So when this input comes in, then you would say, oh, you don't have to go to 6 or 7 or 8, you have to go to 1. But now, you have a problem, you brought in 6 and 7. So, then you'll say, okay, throw these away. So, you will just erase this and, a bubble would go through. And in the next cycle, when 5 is here, 4 is here, a bubble would be here, another bubble would be here, and here you would have instruction number 1. So that means in the execution of this 5-line program, every time you will have 2 bubbles, and that is going to really cause you a problem in terms of your branch or your calculation efficiency. Your CPI would increase. Now, how can you avoid it? So for avoiding it, we are trying to see whether we can predict a branch. Suppose if we had some mechanism which would tell us that the next instruction to be fetched after 5 is instruction number 1, without instruction number 5 getting executed, right? So that is sort of a prediction, and it's a difficult thing. It's almost like a share market prediction, that a particular share value, is it going to increase or decrease? Well, you can get some idea. It's not a total random thing. You may study the company profile, you can study the projections, you can study the company's balance sheet. You can make some prediction, educated prediction, that okay, this is going to do well, or this stock is going to go up or going to go down. And based on that, you play the stock market. Every time you may not win, sometimes you may lose money also. Same thing here. So you try to predict that after instruction number 5, should instruction number 1 come, or you should come out of the loop and instruction number 6 should come in. So for that, there are 2 ways. The first one is known as static branch prediction technique. Now, what static branch prediction technique is, you have got one answer, and the answer is either take the branch or don't take the branch. So it is like asking a parrot that okay, am I going to win or not? Parrot will always say you are going to win, or other parrot may say you are going to lose. Now let us see which one is better. Now, so we saw here that in the static branch prediction, one method is predict always not taken, and the second is predict always taken. So in this particular case, which one would be better to us? Can you imagine predict always taken and predict always not taken? I mean, you have got 2 answers. Which one would be better? Anyone?
Always not taken.
Okay, that is one answer. I mean, the other answer could be always taken, right? Only 2 possibilities. Why always not taken is good?
Because if the loop runs for a large number of times, then if it always takes the predict, then there will be 2 into the number of times the loop runs. Bubbles will be formed, which will be very time consuming. So for large number of loops, it is better to not take the predict.
Okay, predict not taken.
Yes.
Okay, anyone else? Opposing view?
Yes, sir. Like it is predict always taken. Otherwise, if it is not taken, then the thing will be same as the like you showed. Like always the 6 and 7 will come and there will be a bubble form.
Okay, so I mean there are 2 ways: predict taken and predict not taken. Both of them are legitimate static predictions. In which case, either of them would be useful. I mean, your loop has to have some characteristics to use either predict taken or predict not taken. Any rough idea?
Sir, if the loop is being executed a very large number of times, then Predicting that branch will not be taken is a better idea.
Okay, I think you got it wrong. Say, okay, so let us take this example. Let's say this loop is executing 100 times. So, you say that you start with I equal to 0. And then, you say I plus plus and increment I, and then, you stop when I becomes greater than 100. Okay, so this loop should go around 100 times. If you have taken predict always taken, then how many times you will be correct? So when I ask you, when you come at instruction number 5, then if I ask you a question, should I bring in 6 or should I bring in 1? And if I used predictor as always taken, means branch always
100.
taken, then how many times you will be correct?
100 times. First 100 times.
Right. So now do you understand that, probably predict taken might be a better thing, because loops, usually you don't write a loop unless, you do something multiple number of times. And that also sizable, maybe 10 times, 100 times, 1,000 times, 10,000 times. So even, a common sense approach, if we use, then, you can say that, particularly in a loop, usually, it is a great thing, by closing your eyes and, if someone asks you whether the loop will be taken or not taken, you will say, okay, go ahead and take the loop. I mean, most of the time you will be correct. Only at the time of exit condition, you will be wrong. Does it make sense?
Yes, sir.
Okay. So predict taken is normally a great idea for loops. That, you just come here and then, after 5, you ask your predictor, should I go back to 1 or should I go to 6? And then, that predictor would give you one answer. It is not a very smart predictor. It does not, when I say it is a static predictor, means it does not learn anything. It does not learn anything, what is happening to branches, which way the branches are resolving. All it would do is give you one standard answer from copybook that, okay, take the branch, take the branch, take the branch, no matter what. Even for the 101st time when you are wrong, the answer would be take the branch. And then, you will take the branch and you will get a wrong answer. So at the time of exiting, it would be exactly opposite case of this. You will be getting 1 and 2. And then, you will say, okay, you're supposed to actually exit the loop, not repeat the loop. So, 1 and 2, you will have to chuck out. But, that would happen after 100 correct predictions, you will get 1 wrong prediction. So you say, okay, I mean, I saved a lot of cycles by, making correct predictions. So maybe a couple of wrong predictions out of 101 totals or so. That means 101 times, 1 wrong thing, it's maybe less than 1% wrong result. So my predictions are 99% correct. Okay, so does this make sense that, we use predict always taken as a great idea?
Yes, sir.
Okay, but then there is also another thing. And then, now you would also say that, why you should use predict always not taken. So, there are times and chances or places where you would like to use predict always not taken. And, that would be like, escape statements where, you say jump statement where, you are stuck somewhere and, you can't go forward. So you say jump to this particular memory location. And as I told you earlier, you should not write programs with too many jumps or too many go-tos, because, it is going to mess up with your memory architecture, that, your blocks would be now thrown apart and, your cache would be crashing. Some blocks which are there has to be removed. So ideally, as I told you, if you understand the cache now, you want to bring in certain blocks to the cache and use them repeatedly as much as possible before throwing them out. Because throwing out something from the cache and bringing another new block is actually a very time and power consuming task. So now, in your actually this thing, you may say that who would be using static branch prediction? Actually, the ARM7, which you are using in your Kyle compiler, ARM7 TDMI processor made by NXP, is using static branch prediction technique. And it is using a combination of these two. So backward branch predict taken, forward branch prediction not taken. So what it means is, when it is backward branch, that means if it is a loop, you say always take it. And if it is forward jump, you know that this is just an escape clause, and it will not be used too many times. Just in case you get trapped, you will say jump forward. So this is actually a good idea, and this is used in your ARM7 TDMI processor, which you are using. Okay, so this was used 20 years ago, but it is still as good, and it is still used in some of the tiny processors that to improve performance. One thing you can always say, predict always taken is great for branches. So I want to use it, and predict always not taken. People do sometimes write jump statement or somewhere branch forward kind of statement. So this kind of predictor actually plays a very useful role. So even though static branch predictor is not able to learn anything, it is not adaptive. So it does not see that if it is giving you wrong answers, so that probably it needs to change. It can't do that because it is hardwired. But for most of the common tasks, this would serve a great purpose. And we'll see later on that it can be used as a fall through mechanism. So what it means is that fall through mechanism means we are going to study other types of branch predictor which are a little more sophisticated, because not all branches are like loops. There are certain branches are sort of conditional, that if it is even, go here. If the answer is even, go to this particular statement, or if it is odd, go to that particular statement, right? So that means the answer might be oscillating. It is not always go back to instruction number 1 and then execute 2, 3, 4, 5 and then again take a loop. So this might be dependent on the input. So if the input is even, go to a particular instruction, or if the answer is odd, go to some other memory location. So in that particular case, static branch predictor will not be very useful. Similarly, sometimes I will show you all kinds of sophisticated prediction predictors or prediction techniques. And like always, I will also show you that, in certain corner cases, it will go horribly wrong. So in some cases, it will be very, very good. Just like, remember, we talked about replacement policies, that, all replacement policies sound quite intuitive and, quite useful for block replacement. But, I can always give you an example or a corner case where that particular replacement policy would make your program or your execution go horribly wrong, because, you will be throwing out useful blocks and, it will be a mess. So same thing, if such thing happens, then, it always boils down to this, that, after you will have dynamic predictors, which actually learns from the way the branches are resolving and, trying to adjust themselves. But then, if those techniques are giving you horribly wrong answers, then, you fall back to this. And then your processor is usually using this kind of prediction. Again, there is a temporal correlation. That means a branch resolve, the way a branch resolve may be a good predictor of the way it will be resolved in the next execution. So what means is that, we talked about instruction number 1, 2, 3, 4, 5, and so on, 6, 7, 9. And if the instruction number 5, the branch this is a branch statement. If it is resolved once like this, then next time, it is a very good chance that it will be resolved like this. And what is the reason? The reason is that branches are usually 10, 100, 1,000 times repetition. So that means there is a temporal correlation that if a branch which is at instruction number 5, if it is resolved last time it resolved to instruction number 1, there is a great chance that next time also it will resolve to instruction number 1. It may not be always be correct because maybe you are supposed to get out of the loop and still you bring back to number 1, and then you will have to throw away the instructions, and then you have to again bring back instruction number 6 and 7 and then continue with that. The second is a spatial correlation. So let us say there is a branch in instruction number 2, instruction number 6, and instruction number 12. So these are all branches. This is a branch statement, this is a branch statement, and this is a branch statement. So what it says is the way the branch number 12 would resolve would depend on how branch number 2 resolved and how branch number 6 resolved. So based on that, branch number 12 would resolve. So this is different. Temporal correlation is very simple. For spatial correlation, when we come to this topic, I will give you a specific example that, because you always target how branch number 2 resolved. If it says, then, you figure out that, if the branch number 2 was taken, branch number 6 was taken, then branch number 12 would definitely be taken. Or if branch number 2 was not taken and branch number 6 was taken, then, probably you may or may not take branch number 12. Your branch predictor hardware would figure that out. So this is known as a spatial correlation. If anyone has any question, you can stop me and ask the question. So first, we will talk about a very simple predictor, which is known as 1-bit branch prediction buffer. So what is this 1-bit branch predictor buffer? So it would work like this. Okay. So your 1-bit branch predictor before I explain you anything about 1-bit, 2-bit, or any other sophisticated branch algorithm, let me ask you a question. I have got 5-stage pipeline. Where should I place my branch predictor? Which state should have branch predictor? Any idea? See, branch is definitely going to be resolved in execute stage, right? So you don't need to have anything in execute stage. So where should I put my branch predictor so that I can save some cycles?
At the fetch stage.
At which stage?
Fetch stage.
Fetch stage. Okay. Any other answer? Okay. So probably he's right. And then let us try to understand why. Because at fetch stage, say, I'm continuing with the example which I just gave you, that, instruction number 5 has passed on and, has moved here. Now your PC program counter has 2 choices. Either go to PC gets PC plus 4. So that means bring in the next word. So, bring in 6, or you bring in something which predictor tells you. So here your predictor is making a prediction that, bring in, instead of 6, bring in instruction number 1. Then, again, start wondering that, in words, this sounds very interesting and, very intuitive, but how do I actually implement it? So the actual implementation would be in the form of a table. So let us say you are executing a program. Okay. And this is your branch target buffer, or people call it BTB. So how would I do it? So first time when the program is just executing, I don't know which instruction is a branch instruction, because fetch stage does not tell me anything. So I would just wait for it to go. Then, when instruction first has been fetched, and when the fetch stage fetches an instruction, it does not know anything about it. Then when it comes to this particular stage, it would figure out it's a branch statement or not. That's all it can figure out. It would not be able to figure out whether it will go this way or that way. So fine, that information is enough. So you will say that instruction number XXX is a branch instruction. So in this branch target buffer, this side, you will just take account of instructions which are branch instructions. You don't care about algebraic instruction. You don't care about logical instructions. Those instructions are not, will not find a place in this branch target buffer. So only branch instructions will find a mention over here. Now, whether, your program counter says a value of XXX. Now, if the branch is taken, it will give you a different, some value that where, if the branch is taken, where it will have to go. So in the second stage, of course, this thing is empty because it still has not been executed. In the third stage, when it comes to execute, you will find out an answer that, okay, you have to go to instruction number 1 and not go to instruction number 6. So your branch target here would be instruction 1, right? So let us, for convenience sake, I would write instruction number 5. If the branch is taken, it will go to 1, right? If it is not taken, then, of course, it will go to 6. But if it is taken, it will go to 1. Then along with it, because, even this is not good. Where is the predictor? I mean, you are putting something, which is out there that, when instruction number 5 came, it went to instruction number 1. So your hardware is dutifully noting that after instruction number 5, instruction 1 was executed. So then you need something which is known as predictor. So predictor will say that this is, you are going out of your normal PC gets PC plus 4, right? You are not going to 6, but you are going to 1. So predictor will tell you whether you should go here or you should not go to 1, and you should go to 5. So you will go to instruction number 1 only if the branch is taken, right? So if your predictor says taken, it will go from 5 to 1. If it says not taken, then, it will not go to 1, it will go to 6. Is this clear to you? Does anyone have any question? So here's how it will be implemented. So first, you fetch instruction number 1, it went through. Instruction number 1 did not find a place in this branch target buffer because it is not a branch instruction. Then 2 went through, 3 went through, 4, 5. 5 was fetched. At that time, 5 doesn't find a place over here because, the fetch state doesn't know as of now that this is a branch instruction. It will know it in the second cycle or the second round of the loop. Then, when fetch this instruction number 5 goes from fetch to decode, it will say, okay, this is a branch statement. So, instruction now, you will put that memory address. And here, just for sake of simplicity, I'm putting a decimal number 5. Actually, it would be a 32-bit address, but, I'm just saying number 5 would be here. Target, it doesn't know where it would go. That you would figure out after stage number 3, where, your conditional execution would tell you that it will go to instruction number 1. So initially, you will have, when this is, you have not figured out that, it will go to 1, you will start with not taken. Now, you say, why not start with taken? Why not start with a positive frame of mind? Because, you have to initialize your predictor. Would you initialize it to the taken or initialize it to the not taken? So I say predicate to not taken. And why did I choose that? Just like, when you initialize something, put everything to 0, 0, 0. Why you are not putting it to 1, 1, 1? I mean, it doesn't work that way. So you put it to 0, 0, 0. So I'm taking it not taken. Now, understand one thing. When I ask you for a prediction accuracy, I would tell you that, it is a loop which is taken a very large number of times. Now, this particular choice of words has a meaning. Because, for the first iteration, it may not have the value of 5 or 1, or it would give you a wrong prediction. But, over, say, 10,000 prediction, first iteration going wrong is of no consequence, right? It's a small jitter in your result. So when I use the word that loop is taken a very large number of times, that means that initial wobble where, 5 was not known to be a branch, and then, 1, and then, initial prediction was not taken. And next time when it came and, it was taken, so you will say, okay, that is fine. But, next time when 5 comes, here initially it was not taken, but, when actually it is taken, you change it to T. This is how 1-bit predictor would work. And, you will automatically predict that, after 5, instruction number 1 would come. Okay, may I request Parth to turn off his mic? Parth, can you please turn off your mic? Okay, so this is how 1-bit predictor works. So again, going to our faithful example, you are coming to instruction number 5. 5 is a branch statement. So your 1-bit predictor, this is your 1-bit predictor, which is putting a value here. And 1-bit predictor is only telling you take or don't take. But as opposed to a static predictor, which would always give you the same answer, 1-bit branch predictor, this is a class of predictor which is known as dynamic. And dynamic predictor means a predictor which would learn. So it would learn that, okay, last time it was not taken, but, my prediction was wrong. And, actually it was taken. So I would put it as, next time I would put it as taken. So for next 100 times, or, a large number of times, whenever 5 comes, your prediction, because it is taken, last time it was taken. So this time also you say take it. So then, you will go to 1. So it has learned from previous case. So that means you will always go back to taken, taken, taken. And when you come out, you will say not taken. Is this clear to you? Okay, I hope it is. So let us go one more time. So now I'm talking about a predictor which has got, say, a loop which is executed 100 times. Okay. If I use 1-bit predictor, how many times my predictor would give correct answer. And I'm assuming that you start with your predictor as not taken. Why? I mean, there's no particular reason, it's just a convention. So how many times will be wrong?
2 times.
2 times.
Okay. So couple of people says that it is going to be wrong twice. So let us understand how it will go wrong twice. So the first time, and I'm assuming that your prediction table is filled with one instruction. So I mean, once cycle has taken place, so your predictor table now looks like this. But this is your PC is 5, then your target is instruction 1, and this is your prediction. So the first time it is no, because that's how we would initialize it. And first time it will be a wrong thing, because of course you would take the loop. So the second, then it will say for when it comes to the second loop, I would, and then predictor would change its state from not taken to taken. So basically not taken and taken means not taken usually means 0 and taken means 1. It's not necessary that you put taken as 1 and not taken as 0, but this is convention. So similarly, like your logic 0 is usually taken as 0 volt and logic 1 is taken as some 3 volts or 5 volts or 1 volt something. Why can't you take 1 volt as logic 0? I mean, of course you can, right? But this is a convention and it is intuitive. So your next time it will be taken. So the second time in the loop you come, you will be correct. Third time, because you are correct, you don't need to change your prediction. You keep it as taken. And then, for the fourth time, then 99th time, it will be taken all the way. And the 100th time, it would also be taken. And for the 101st time, because the previous prediction was taken, you would take the branch and then you will figure out that, oh, you were wrong because condition is not met. That means you are going over 100. You are not less than 100. So that means you will be wrong. So you'll be wrong while entering the loop and you will be wrong while exiting the loop. So if you use 1-bit predictor like this, then you will be wrong once while entering and once while exiting. Does anyone have any question? If you have any problem, please ask me now. Okay.
Sir,
So yes,
sir, where will the predictor be over here?
I'm sorry.
Where will the predictor be?
Okay. So in the hardware, I mean, it could be anywhere, but we are putting the answer over here. So this is if, so I mean, this table, you can read it like this. If my PC address is 5, then I will go to target as 1 if my predictor is taken. And I will not go to target as 1 if predictor is not taken. So if this is not taken, it will go to 6. If this is taken, then 5 will go to 1.
Because means the fetch stage will take means fetch the
So
instruction
I'll tell you. So
after
as soon
after
as
looking the buffer table.
correct. So right now the PC value is 5, right? So fetch stage would read that the previous PC was 5, and that it already knows because it has fetched it. So before fetching the next instruction, it would quickly glance through this table, and it would say, oh, okay, when the last PC was 5, the target I jumped to 1. Now, whether to jump to 1 is correct or not is seen through this, not taken. Or it could be taken. So if the prediction is taken, then it would say, okay, the next PC should not be 6, but it should be 1. So the fetch stage would fetch 1.
Okay, sir, but wouldn't it take some time to look look at the buffer table?
Yes, it does. So that's why I said that initially when you start studying the computer architecture and first, then fetch is a very simple thing. You'll think that okay, on fetch all I have to do is go to instruction memory and fetch it and bring it back. But in reality, fetch stage has to do a lot of work. So the first lot is prediction. So this part is prediction. Then actual fetching, which is over here. And in fetching now you have studied memory hierarchy, that finding something, if it is not there in the first level of cache, it has to go to in the second level of cache. So in all modern processor, your fetch stage is broken down into 2 stages. So you will find as fetch 1 and fetch 2, right? So I mean the work of, so that your processor can run at a higher cycle speed, because normally fetch stage has to do a lot of work. Does that answer your question?
Yes, sir. Yes, sir. Means,
I mean, if it is not clear, you can ask again.
and sir, this prediction will be made after the execution stage.
Okay. No. Yes. I mean, let me clarify. The first prediction, whether to take or not take, you will find out only after the first execution of the loop, when you come to execute stage. Now, till you have not come to that particular stage, you will put your predictor as no. Correct?
Yes, sir. Yes, sir.
I mean, because
Yes, I
we
can
just
understand.
one value has to be there. Either you could have put taken, but
No, sir.
by
Means
convention, we
I
have
was
put it not
asking that
taken.
after after it is initialized, means the further predictions will be made after means each time the execution stage is reached, right, sir?
Okay, so every time it would look at the previous result. If the previous was not taken, so it would go like this. If you want to do this problem methodically, then it would work something like this. So this is your first loop, second loop. These are not instructions, these are loops. Third, fourth, fifth, sixth, seventh, this instruction. Okay. So this you can write as prediction and actual, because prediction may not always be right. So let us start from first one. First one, you assume that it will not be taken. Why? Because it's convention, you start with not taken, but the actual outcome of the loop was taken, right? So now your predictor is learned. So now this actual outcome would be the prediction for the second branch. And why so? We are using this temporal correlation. which says the way a branch resolves may be a good predictor of the way it would resolve at the next execution. So we are using this temporal correlation, property of temporal correlation, and which even by inspection, you know, that works very well in a loop. So now your next prediction here is taken, and the actual outcome naturally is taken. So, you know, this would be prediction for the third loop, and the actual outcome would also be taken for a large loop. Then, you know, this prediction for fourth loop is taken, and actual outcome is also taken, so on and so forth. So when you come to say 100, and then I assume that till 100 you are supposed to take, the prediction was taken and actual outcome is taken. So for 101st, you put this prediction is taken, but the actual outcome would be not taken. Okay. So then, you know, you get out of the loop, and then you go to 6, 7, 8, 9, and, you know, whatever, whether there's a next branch, it will come into another loop table. So does this make any sense to you?
Yes, sir. Yes, sir.
So that means that, you know, the actual outcome of that loop the previous time would become a prediction for the current loop. So this is taken. Actual outcome is also taken. So that becomes a prediction for the next loop. That is the third loop. And, you know, if the actual outcome of this third loop is also taken, then the prediction for the fourth loop would also be taken. And, you know, this is due to the principle of temporal locality. Here in loop, it is very nice that, you know, you are always getting taken. But, you know, I can give you one example. And say the example is, I mean, I've given you a good example. I can give you one bad example, but, you know, let me just wait. I don't want to take the thunder away. Can you give me a bad example of this kind of predictive behavior? So this is sort of a good example.
Sir, an example can be every alternate times that it is taken and not taken. Can be a bad example.
Okay. So let us say, as Tarang said, that I'm doing a loop. And, you know, this loop is taken 100 times, and this is loop number 1, loop number 2, loop number 3, so on and so forth. And, you know, suppose I have written a program that, you know, the alternate result is outcome is 0 and 1. And then, you know, I've written a branch that, you know, if it is 0, then go here. If it is 1, then go there. So if my outcome is 0, and you know that outcome of 0 and 1 comes alternately. So the first time I've taken, my answer is not taken. Now the actual input was even, right? So a particular branch, if it is even number, then, you know, you're supposed to take the branch. If it is odd, then not take the branch. So let us say we are starting with an even number. So we are starting with 0. So then, you know, your actual outcome is not taken because you are not supposed to take the branch for even number. You are supposed to take branch for the odd number. So because this actual outcome of the first loop is not taken, your prediction for the second one is not taken. But since the result for the second one would be odd, then, you know, the branch would be taken. So your prediction is wrong. So this is a wrong prediction. So now you will say, okay, now I have learned. Now I will say the prediction is taken. But lo and behold, at 3, it is the number is again even. So then, you know, you are not supposed to take the branch. So now I'll say next loop would, and then, you know, actual outcome would be taken. And then, you know, you predict that next one would be not taken. And then it is, I mean, taken and it is not taken. So you will be wrong every time, right? So this is not, I'm not sure, I'm telling you that 1-bit branch predictor is really bad. But I'm just showing you that there is one possibility, which is like a coin toss kind of probability, where regularly you are flipping between taken and not taken. In that particular kind of thing, which is a corner case, you will get awful result that every prediction would be wrong. Does it make sense to you?
Yes, sir. Yes, sir.
Okay, others also can answer if they understand or don't understand. Okay, so
Yes,
I
sir.
don't want to go to 2-bit predictor today because there is not much time left. But you can extend what your 1-bit predictor is saying. 1-bit predictor is answer is taken or not taken, right? So it is saying it's just a black and white world. Either you take the branch or you don't take the branch. Now people have said that if I use 2-bit predictor, will it be any better? Now that if you do 2-bit predictor or anything which is 2-bit, that means it will give you 4 states. 1 bit will give you only 2 states, right? 1 and 0. So that means taken, not taken. Whichever one want to call as taken. Normally we say 1 is taken and 0 is not taken. But what if it is like 2-bit? Then it is like 0, 0, 0, 1, 1, 0, 1, 1. So, okay, you may say 0, 0 is not taken and 1, 1 is taken. Then what about 0, 1 and 1, 0? I mean, you have to give them some names, right? Otherwise, what if you enter into 0, 1 state or 1, 0 state in a state machine? You can't have indeterminate stage. And same thing, you say you can have 3-bit predictor, so it would give you 8 states. So what do you do with first and last? And what about the remaining 6 states? You have to give them some name or some action. So next class, when we study about 2-bit predictor, we are going to talk about how a 2-bit predictor would work. And 2-bit predictor is generally used in even modern computer system. 1